Chapter 2 is kind of a repetitive chapter, but I go into more details regarding the structure of the universe. The primary claim is that the universe is not homogeneous. I think that this is a very obvious claim. It requires looking around and verifying that the universe is not homogeneous. You can look to your left, you can look to your right, and you can see that things are of a varying mass density. Mass density is a scale-dependent variable, which means you must include the volume to know the mass density. And as the volume increases, mass density decreases in our universe. This is because it's isotropic. Now, isotropic means that it's kind of constructed in a similar manner. This is you can look around. Isotropy is also verifiable just by looking around. You can look through a telescope and you can see that no matter where you look in the universe, it's constructed of stars and galaxies. Cosmologists would claim that I am misunderstanding their point, that on average it's homogeneous, that of a scales of a certain size or larger are homogeneous. I got Claude to list out the arguments against me, the arguments in favor of homogeneity. And one of the things that it listed was that scale dependence is acknowledged. It says the field explicitly recognizes that the universe is highly inhomogeneous at small scales. The cosmological principle applies only above a certain homogeneity scale. But this point undermines the point it's trying to make. It contradicts itself. Scale dependence continues forever. So if you increase the scale, the density is going to decrease. It's not homogeneous. Whatever preferred scale you want to choose, you assign a homogeneous mass density to it, then I can just double the size of it, and now the density is different. Something else they claim is that it's averaging. It's statistical averaging. So if you're looking at those clumps over there, they are of a high density, but then there's voids over here, and this has a very low density. And this averages out. This is not what we're doing. That is not, let me repeat, that is not how you do cosmology. Voids are not the subject of interest. Voids do not create geometry. Voids do not have gravity. Voids are not what we're modeling. It's weird that I have to make this point, because it's like talking about bananas. We're talking about mass here. We're not talking about voids. We're talking about objects. We're talking about the universe. We're not talking about emptiness. You can average emptiness into anything and this is crazy to me. Now it's one thing if you want to talk about a certain region and you've got a giant void in one area, then yeah, you can take that into account. But really, you don't have to take that into account. You just have to take into account that all the mass is on this side or clumped in over here. You want to model where the mass is, not where the mass isn't. But even if you model where the mass is and then you have a place where the mass isn't, we don't look at those things. What we're talking about here is essentially the data coming from, how do we decipher the data coming from all of these objects in the universe? In order to decipher this data, you have to have a paradigm, a model. And so that's why this stuff is important, is because we want to create an accurate model to represent the data that we're receiving. That way we can decipher it and actually verify theories and ideas and things, whatnot. And so if you're looking at a star, if you're looking right at a star...
Now, of course, if you look right at a star, it looks a little different than if you look at away from the star.
The direct line of sight between your eyes, and that star, should we use homogeneity for that geometry? No. No. You know why? Because that star is in the center of this metric. It's the beginning of this null geodesic that you're looking at, that you're analyzing. I mean, an observer and a star is pretty much the most basic setup that you can create. And if you create just imagine an entire universe that's only has one star and one observer. And then now, like, obviously it's not homogeneous. This is not a homogeneous universe that I just described. How do we make it homogeneous? I don't even know how. I don't even know how to make it homogeneous and be simplified scenario where it's just a star and an observer. Like, I can't even describe a situation where it's a universe with a homogeneous distribution of stars and one observer. I mean, you can kind of imagine it, I guess. But the mass density is still scale dependent, and so it depends on the distance that the star is from the observer. Take a look at this graphic. I got ChatGPT to make a graphic for us. So there's several lines here. The shaded line, and I guess this is orange with a brown tan shading around it. The very bottom line. This is the homogeneous line, okay? And ChatGPT says that there's voids and then there's clumps of matter. And that's why this line is not straight. Like, it's averaging out over different radii, including various objects. And so it's not a straight line. Okay, that's fine. I don't agree with that. We shouldn't be modeling the voids, like I said earlier. But you can see that this is not homogeneous. If you ask a cosmologist to draw a line if you just create this chart here with the radius and the mass density, and you say draw the line for homogeneity, they got to draw it straight line. It can't be sloped at all. But then they say that, there's big massive objects, so we can have a little bit of a slope. And so that's how we get this line. But we're not modeling the voids. You can model the voids if you want. Look, if you want to model the voids, that's fine. I'm sure there may be a purpose for that. But for my interest, I want to decipher the redshift, the cosmological redshift. And so that's why this is important. Is we need to know how much gravitational redshift there is. Because this green line, this line that's very, very close to the one that includes voids, which is absurd. The line that includes voids is very close to this 1 over R line. This 1 over R line is the green line. Is that green? I don't know. ChatGPT uses the worst colors. It's this line right here. This is 1 over R. Now what that means is that the density is proportional to 1 divided by the radius. So if we're talking about starlight, we're talking about the distance the star is from your eyeballs. And so that scale dependence part really comes into play here at the Hubble radius, where these lines are intersecting. Now these are all normalized, so we can make them intersect wherever, but I have them intersecting here. These lines, the straight lines, continue. Like, you can just put a ruler on that and make them longer using the same slope. But this homo line will stay straight. And that is physically unrealistic. That's what I mean. It has to be scale dependent. Okay? It has to be. Because if it stays straight, then the objects that we're including after that radius, after that distance, for the larger scales, the objects we're including in the new additional scales have got to be more dense than the objects in the other scales that we just checked. Or there has to be more of them. I actually have another graph. Let me pull this up. Okay, so with this one, they're normalized where they start at the same place, but this is just as good of a visual, if not better. The 1 over r line, that's the 1 over r is what I'm proposing. That's the blue line. It's on top now. It's the same slope. All the lines are the same slope. This is just normalized differently. So now you can see there's a cross. The homo line crosses the 1 over r line somewhere, and the homo line will continue to stay straight all the way through, and the 1 over r line will continue to capture the scale dependence of mass density. And so one is real, one is not real. So why does this matter? Some of you may be like, what does this matter? Like, you're just comparing lines. I don't understand. 1 over r has a gravitational redshift that is linearly dependent. Okay? It's, you can align it with Hubble's law. The homogeneous line is supposed to be no gravitational redshift. Well, not zero, but it would actually technically be zero if it was truly homogeneous. It would be zero gravitational redshift. But the claim from cosmology is that there's relatively no gravitational redshift across large scales because there's no change in potential across scales. This is nonsense because the line we just drawed, the line that shows this averaging, is actually not homogeneous because they see that this is having their cake and eating it too makes it difficult to argue against because they're saying it's homogeneous, so there's no gravitational redshift, and you're like, it's not homogeneous. And they're like, well, of course it's not perfectly homogeneous. Okay, well then draw the line. And this is the line they draw. This line that they draw literally shows that there's a gravitational redshift. And so I don't really know how to argue except to just, I guess, state the obvious here. This is pretty dang simple. I think it's so simple that it's easy to overlook this such a simple thing that it's easy for them to just ignore because they're trying to model the entire universe. They're not thinking about looking at a star. When you're looking at a star, it's different. This is different than modeling the universe. And so when you're looking at a star, no matter what, across large scales, unless you are a giant black hole. Okay. But for just a human, no matter what, when you're looking at a star, there's going to be a distance proportional gravitational redshift. No matter what. You cannot avoid it. I don't care what any expert says, they're wrong. This hillbilly in North Carolina knows the answer. And I am being truthful about this. I have studied gravitational redshift for 16 years. 99.999% of physicists will say I'm wrong. They are wrong. I can't do, I have nothing to wager. I'm putting my credibility on the line and I have no credibility. And so this is really easy for me to say and it's really easy for nobody to care. But I don't like making videos. I don't like talking to people. I don't like writing books. I don't like doing this stuff. I do not. I promise you. I'm not doing this to gain fame or fortune or any of that. I'm doing it because I'm obligated to tell the truth when science is ignoring it. Oh, Lord, I got a little passionate there. I don't know. man, it's rough. This is a very difficult subject because it's a difficult enough, it's complex enough and technical enough so that the average person can't quite grasp it without spending a significant amount of time. But the experts can't overcomplicate it so much that they don't understand the simple parts. That the basic assumptions that build the entire field, they cannot question those. And I understand it's like biology questioning Darwin. But this is much different. This is actually much different because Einstein struggled with this formulation himself. He knew it wasn't good. He didn't like any of it. It's just difficult to think about how to model the universe. But you don't model the universe. You model the geometry, the null geodesics. This is how you do it. So let's go to chapter 3. Okay, I hope you're enjoying this. Make sure you subscribe because I've got more stuff coming out. And this is commentary, so I'm strictly speaking about each chapter in these videos. But I will be releasing, after I finish uploading the book and doing a commentary for all of the chapters, I'm going to be making videos in a different way, covering many different topics that are outside the book. Thank you so much for listening. Yeah. Bye.